Hi, I'm Maggie Farris, and I will be presenting on Chapter 18, the cardiovascular system. So what does the heart do? The heart is a dual pump, and the right side serves the lungs and the left side serves the body. The pulmonary circuit is the right side, and it moves deoxygenated blood to the lungs, whereas the systemic circuit, the left side, moves oxygenated blood and nutrients to body tissues. Blood flows through the pulmonary circuit first, and then the systemic circuit, and then it repeats. There are four chambers of the heart that receive and pump blood. The right atrium receives blood from the body, and the left atrium receives blood from the lungs. The right ventricle pumps blood to the lungs, and the left ventricle pumps blood to the body. The coverings of the heart include a double-layered sac called the pericardium, the outer fibrous pericardium, which protects and anchors the heart, and then an inner serous pericardium, which has two layers with fluid in between, and this helps prevent friction during heartbeats. The size of the heart is about a fist, and it weighs less than a pound, and you can find it in between the mediastinum and the lungs. It tilts slightly left, and its apex points towards your hip, and the base points to the right of the shoulder. The heart wall consists of the endocardium, the myocardium, and the epicardium. The endocardium is the inner layer, and it lines the inside of the heart chambers and valves and helps reduce friction. It also keeps the blood and the heart separate. The myocardium is the middle layer, and it's thick and made of muscle. Its job is to pump blood and contract. The epicardium is the outer layer, and this is a thin protective layer of connective tissue. It contains blood vessels, lymphatics, and nerves, and this supports the heart muscle. It also produces pericardial fluid to reduce friction. The atria. The right and left atrium are upper chambers of the heart that receive returning blood. The right atrium receives deoxygenated blood from the superior vena cava and the inferior vena cava and the coronary sinus. It has a smooth back wall and a rigid front wall with pectinate muscles. The left atrium, however, receives oxygenated blood from four pulmonary veins. And attached to it you can find the left auricle, and this is made of pectinate muscle. This is there to increase the atrial volume. Atrioventricular valves, or AV. The right AV, or tricuspid valve, is between the right atrium and ventricle. The left AV, or mitral valve, is between the left atrium and ventricle. These help prevent backflow into atria when ventricles contract. They are anchored by chordae tendineae to papillary muscles. They open when the heart is relaxed and close when ventricles contract due to rising pressure. Semilunar valves, however, include the aortic valve and the pulmonary valve. You can find the aortic valve between the left ventricle and aorta. The pulmonary valve is between the right ventricle and the pulmonary trunk. These help prevent backflow into ventricles after contraction. They're made of 3 half-moon shaped cusps, and they open when ventricular pressure rises, and they close when blood starts to flow back. So here's how blood flows through the heart. It starts at the right atrium, then the right ventricle, the pulmonary trunk, 4 pulmonary veins, the left atrium, left ventricle, and aorta, as shown in the picture on the right. Basically, blood flows from the atria to the ventricles to the great arteries. The right side, the pulmonary circuit, to the lungs, and the left side, the systemic circuit, to the body. Pulmonary arteries carry deoxygenated blood, while pulmonary veins carry oxygenated. The left ventricle has thicker walls due to higher resistance in the systemic circuit, and both sides of the heart pump at the same time. Cardiac muscle cell structure. Cardiac muscles are striated like skeletal muscle, but short, branched, and interconnected. They only contain 1 or 2 central nuclei per cell, and they are surrounded by endomysium and are connected by fibrous cardiac skeleton, which gives anchor points for contraction. Intercalated discs and synctium Muscle cells are connected by intercalated discs. Desmosomes hold cells together during contraction, and gap junctions allow ion flow and synchronized contraction. The entire myocardium acts as a functional syncytium. The mitochondria and myofibrils. Cardiac cells have many mitochondria and about takes up 35% of the cell's volume. Because of this, it makes them highly resistant to fatigue. Cardiac cells also contain myofibrils, which contain Z discs, A bands, and I bands, and are made of sarcomeres. Sarcomeres vary in size, which allows for more spacing, and this makes the banding of the cardiac cell different from the skeletal cell. How cardiac muscles different from skeletal. Cardiac muscle contains pacemaker cells that can generate electrical impulses on their own, making the heart self-excitable without needing nerve input. Cardiac muscle cannot undergo tetanic contractions because it has a long refractory period, and that allows the heart to relax and refill in between beats. Calcium ions enter cardiac muscles cells from the extracellular fluid, which then triggers additional calcium release from the sarcoplasmic reticulum inside the cell. Cardiac muscles rely entirely on aerobic respiration for energy and using oxygen along with fuel sources like glucose, fatty acids, and lactate. How the heart beats. The cardiac cycle includes all the mechanical events that occur during one heartbeat, which lasts about 8.8 seconds at a normal heart rate. During mid to late diastole, the ventricles fill up with blood while the atria contract, and this helps push the blood down. During ventricular systole, the ventricles contract. This starts the isovolumic contraction phase and is followed by the ventricular ejection phase, which blood is pushed out of the heart. In early diastole, the ventricles relax and remain closed until the pressure in the atria becomes higher than the ventricles. This causes the AV valves to open the cycle and to restart. Changes in pressure throughout the heart control the flow of blood and the opening and closing of valves. Cardiac output. Stroke volume. Stroke volume is the amount of blood ejected by a ventricle with each contraction, and cardiac output is the amount of blood pumped by each ventricle per minute. You can calculate cardiac output by the product of stroke volume and heart rate. The degree to which cardiac muscle cells are stretched just before they contract is called the preload, and it helps to automatically control stroke volume. In a normal heart rate, the higher the preload, the higher the stroke volume. This relationship between preload and stroke volume is called the Frank-Starling law of the heart. Stroke volume and venous return. Venous return is the amount of blood that fills the heart before it contracts. Stroke volume can be calculated by EDV minus ESV, and those are end-diastolic. EDV is end diastolic volume, and that is the amount of blood in the ventricles before contraction. End systolic volume is the amount remaining after contraction. Anything that affects the heart rate or blood volume can also affect venous return and therefore influence stroke volume.